Hey, welcome back. So we've got our next piece to our reaction rates that we need to put into place. And so we need to stop and think about what this means in order to react. We've got to have some particles. Some particles actually come together and start to collide, break bonds, form bonds, and then start to make our products. And so if we had this generic reaction where A and B and C all reacted together to make D, this wouldn't work. It just wouldn't. We see reactions written this way all the time because we're just oftentimes thinking about, okay, if I put this stuff in, what do I get out? But if we stop and think about the collisions, things get a little funky. So what we've essentially described is what we call a three-body collision. We've got three different particles all colliding simultaneously in just the right orientation in three-dimensional space to give us this new thing, this new D for this generic reaction. And not that it's impossible, it is just statistically speaking, nigh impractical. It would be incredibly rare to be able to get three particles to simultaneously collide in three-dimensional space with the right orientation and energy to be able to do this. And so because of that, we got to take a step back and actually think about what is happening to all of the particles in order to give us the change that we are hoping to see. And so really when we come across these mechanisms, there's kind of three questions we ask ourselves when we think about what could be giving us the change we are seeing. So the first question is whether or not, as we've got it written, is this reaction a uni or bimolecular collision? Do we have just one thing or two things colliding? If so, awesome. That can happen. Two things, they collide all the time. One thing, one big molecule breaking apart happens all the time. But in order for our reaction to, or our mechanism to be valid, it has to either be a uni or bimolecular reaction. Our next kind of criteria or big question we should ask ourselves when we're looking at these types of what we call mechanisms is, do the steps we have proposed add up or sum to the overall reaction? Is what we've described happening give us the reaction we actually see happening in the beaker or in the reaction? Not unlike what we saw in our thermodynamic unit in college chem, where we kind of did the Hess's law to sum stuff up. That's what we're looking at here. And then the last question is, we collected some data in the lab and we know how to calculate a rate order or a rate law. Does what we've proposed for our mechanism or our steps, do our steps actually match what we see happening with our rate law? Does it actually make sense with what we see? Now, got to define a little bit, and we'll look at a couple examples. I promise it'll make sense before we're all said and done here. And so our first kind of elementary step, or our first piece to our puzzle as we start to think about our mechanisms, is we can have one substance turning into a product. This would be a unimolecular reaction, that there's only one molecule, you got one big A, changing or breaking into our product. We call that unimolecular. If we wanted to write a rate law for this particular step, because we have what's called an elementary reaction, this little reaction here will only be ever affected by the amount of A you've got. And so for these elementary steps, I know we said earlier you can't do this. For elementary steps, for these parts, we're actually going to pull the coefficients and use those for our rate law. I know I said don't do that. For reactions in the lab, we don't do that. For proposed mechanisms, we're allowed to do that because this is the only thing that could effectively be changing the rate. We could have two A's reacting together, combining together to give us a product. If the first one is unimolecular, this one is bimolecular, our rate law would actually then be second order, that we've got two A's reacting simultaneously to give us a B, and so we would express that as second order with respect to A to give us our overall rate. We could also have two things colliding. This would still be a bimolecular reaction. It would still be second order overall. It would just be first order with respect to each of the reactants. And technically, yeah, you could have what we call a termolecular collision. But again, if your mechanism is here, it's a bad rate, it's a bad step. This will not happen within our chemistry curriculum. It's going to be here if it's going to be a good proposed step. And again, the goal is, can we think about how the particles might be colliding to give us this change that we're seeing, especially if there's more than 2 different reactants taking place in the reaction. So again, this is one of those pieces where it's almost easier to kind of see an example and kind of talk about what's going on here. So here we've got a proposed mechanism. So okay, we got this change taking place in our beaker, in our reaction, in our lab. Would these steps, if these are the proposed steps, would these explain what we're seeing happening in the beaker? And so kind of the first question is, could we write the overall balanced equation? Because I think we've got what we call an intermediate. We've got our first species breaking apart. For our second step, one of these chlorides is reacting to give us our final 2 products. If we were to sum this, we would call our chlorine or chloride here our intermediate. Got made in the first step, but then immediately used up in the second step. It's an intermediate. We don't actually see that. We didn't put it into the beaker. We don't get to take it out of the beaker because it got made and used up all within the same reaction. And so if we were to kind of look at our sum here, we've got 2 of those NO2Cls on the reactant side, excuse me. We've got 2 nitrogen dioxides and a chlorine on the product side. So this would be the overall reaction, and here is how we have described how it might actually be reacting to give us this overall reaction. To determine the molecularity, we're going to look at our reactants and say, what type of collisions do we have taking place in this particular step? Here we've only got 1 species. We call this a unimolecular reaction, 1 thing breaking apart. Here we've got 2 things colliding. We call that a bimolecular reaction, that we've got 2 pieces. And so, as written here, this is awesome. Like, this could totally work if we're thinking about how our particles could collide. We would oftentimes then check, does this match what the overall reaction is? And then we could go and kind of take a step further and write a rate law for each of our steps. So if we wanted to, this could be our first rate, call it rate 1. It would have some constant, we'll call it K1. And it's just going to be equal to kind of with respect to the only thing reacting, that NO2Cl. There's only 1 of them, so it's first order with respect to that first species. We could write a second rate here for the second reaction. We would have our NO2Cl and then our Cl molecule that we had in that second reaction. So just looking at how we can start to kind of assign our rates to our different molecular steps. Now this becomes important when we start to think about what did we actually see in the lab? Based on the data, how does this actually happen or occur? Cool, how are we doing? Example, hopefully good. If not, go back, rewind, review, refresh. We'll get it. As a reminder, PowerPoint is also available on the website. Cool, let's look at another example here where we kind of introduce this idea of our overall rate of our reaction. So here's what we know. We know that at the end of the day, we put in some nitrogen dioxides, they react with some fluorine, which there's only a couple labs in the nation that actually use fluorine gas, straight up, because of how poisonous and corrosive it is. But for the sake of example, we're going to use it. And then we're creating 2 of these NO2F molecules. And this is not going to work as it's written. As it's written, this is a termolecular reaction, a 3-body collision. It ain't gonna go that way. So we're describing some steps or some mechanisms to say what could happen in the beaker to actually get us from these starting substances to our final product. And then we actually went out, we collected some data, and we got a rate order based upon measuring the change in concentration over time. We ended up getting this experimental rate law. So now the question is, if this is what we have proposed, we said, here's what we think actually happens with these teeny tiny molecules as they're bumping into each other in 3-dimensional space. Here's what could be happening to give us this reaction that we're seeing. We've got 3 questions that we should ask ourselves. First of all, are our steps either uni or bimolecular? First reaction, we've got 2. Second reaction, we've got 2. Both steps are bimolecular, 2 things colliding, totally works. Totally works. So kind of molecularity, we're good. Second question, do these steps actually give you that overall reaction? For that, we would sum them. I think we've got another intermediate here. We've got this fluorine molecule hanging out. So that would be an intermediate. We made it, but then immediately use it up, so we didn't put it into the reaction. We don't get to take it out of the reaction. It just is kind of helping with this process. We got, looks like 2 NO2s plus an F2, giving us 2 NO2F. Oh, look at that. Woo! Cha-chink. Cool. Second check. We're good. The third check is, as proposed, would these rates actually match what we're seeing with the experimental data? For that, we got to write our rate laws for each of our steps and see what we got going on. For this first one, rate 1, we got a K1 that's going to be, this first, we got rate constant times, looks like the nitrogen dioxide concentration times fluorine concentration. And for our rate 2, we have some new rate constant where we've got our NO2 and our fluorine molecule. Cool. Cool. But we've made a distinction here. We said we think this first step is our slow step. We sometimes give this a special name. We'll call this the rate determining step. So what we end up having here, we put all of this stuff in the beaker, and this first reaction takes some time. Or we might say it has a high activation energy. We're thinking about our diagrams. We've got a two-step mechanism where that first step has a very, very high activation energy, which means we got to get over that first hurdle before anything can happen. But once we're here, we already have enough energy to get past the second hurdle, that fast step. So really, the overall reaction rate, sorry, this is our reaction progress. This is our energy. Our reaction here is really kind of being held up by that first slow step. And so we actually call it the rate determining step. Once we get past here, we're immediately going to get to our products, which means for this reaction, this K is got to equal our slow step. And if we look, as proposed, it does. We don't have to worry about the second one because it will automatically react as soon as we get over that first activation energy. And so, for our rate determining step, it indeed matches that rate law that we had from our experimental data. This mechanism, as proposed, this mechanism would serve to explain what we see happening with the actual particles way down at that little elementary or atomic level as they collide in our beaker, or in this case, in our gaseous balloon or flask. Now, this is kind of nice because our slow step was first. We would technically have our intermediates here, and then we make our final products. Hopefully you're keeping in mind that this will be an exothermic process because our products have less internal energy than we start with. We have a negative delta H of the reaction. Sorry. Cool. I guess a little trickier when it's reversed. Let's take a look at one of these. Cool. So let's say this was our next example. Let's take a look at this. If we're thinking about this in terms of our graphical analysis, here's what we've proposed. Again, we've got our reaction progress and our energy. What we've said is that we've got kind of two steps. The first one was fast and reversible. We had two particles reacting to make this nitrogen trioxide, but then that breaks back down. But a couple of them, if they have enough energy, can then do a second reaction. Note kind of why these arrows, we'll talk more about that when we get to equilibrium, but that's kind of what these arrows are starting to tell us. So if we were thinking about it in terms of the energy, we were saying we've got a small first step, not a lot of energy to get that first one to go, it's pretty fast, and then a large second step. Okay, cool. Question becomes, does this explain what we see for our overall reaction and the rate as we have measured it based, again, on our experimental data? We got our checks. We got our three checks. So the first check is are all of our steps either uni or bimolecular? We've got two particles. This is bimolecular. We've got two particles also bimolecular. We've got two things colliding. That checks out. This would actually happen. We could make this work. Next question is, do our two kind of elementary steps get us the reaction we're hoping to get? I guess the question is, are there intermediates here? I believe there are. Cool, so the NO3s get to cancel out. We've got NO, and we got 2 of those NOs reacting with an oxygen to make 2 NO2s. Hey, cool. I'm being a little lazy here and leaving my state symbols off. Apologize for that, but getting us through the video. This second check checks out. Now the question becomes, does our rate work? So let's write some of our rate expressions, our rate laws, excuse me. Rate 1 is going to be our K1 times our NO and our O2. Rate 2 is going to be some rate constant times, it's like NO3 and our NO. Get those back in here. Cool. Now the question becomes, does the slow step, does the rate determining step, does that slow step, one in charge of the overall reaction speed, does its rate match the experimental rate law? And as we have it written here, it doesn't. But we have a bigger problem. Remember what our rate measures. It's a change in concentration over a change in time. Take a look at that rate law as you've got it written here. What was NO3 in our beaker? Or let's back up. Did we actively, for this reaction, add the nitrogen trioxide to the beaker? We didn't. It was intermediate. We didn't have no control over how quickly or slowly that NO3 gets made directly, because the NO3 is getting made by our other 2 reactants. And so we get to substitute it. We're going to take, because these were the 2 concentrations that were actually making that nitrogen trioxide, which means really if we were to sub here, we would have NO times our O2 times our NO. When we substitute in the 2 reactants that are actually making that intermediate. Oh, well, I guess if we have 2 terms that are the same, we can combine those, and it would look a little something like this. Now I return to the question, does our rate law, as written, match the experimental rate law? It does. So when we start to write our rate laws, we don't get to use the intermediates. We got to sub them out for the reactants that made that process. We didn't have to worry about it on the last one because the first step was the slow step. We didn't have to worry about how much intermediate was made. Here we do have to take that into account because we have to have that intermediate before the slow step can actually progress. Cool. Now this is threw a lot at you real quickly. I want to give you some time to kind of work through some of these examples. We'll be coming back with questions here in a little bit.